Hello everyone, welcome to my YouTube channel TechSpot. This is me, Harish Goupale. So basically in today's video we are going to discuss about the encoder, and also we are going to implement RTL Design Implementation of 4:2 encoder by using System Verilog. If I talk about working and functionality of encoder, so it is one of the combination circuit and it converts one of the many input lines into the binary code which will represent one active input at a time. Okay, and it has 2 to the power n inputs and n outputs. Means if the value of n is 2, then 2 to the power 2 is equal to 4. So 4 inputs will be there, as n is the output, so 2 outputs will be there. Okay, based on that we can categorize different types of encoders such as 4:2 encoder and 3:8 encoder. If I talk about 4:2 encoder, you can see the block diagram. Okay, it has 4 inputs and 2 outputs. The inputs can be I0, I1, I2 and I3, and output can be Y0 and Y1. If I talk about functionality, so if my I0 is active, then output Y0 and Y1 both are low. Okay, as I told you, one of the input can be active at a time. So if my I1 is active, that time my output Y0 is high and Y1 is low. Similarly, if my I2 is active, then output Y0 is low and Y1 is high. And if my input I3 is active, then both the output Y0 and Y1 both will be high. Okay, even you can see the truth table. 4 inputs are there, that is I0, I1, I2 and I3, and output Y0 and Y1. Okay, as I told you, one of the input can be active at a time. So if my I0 is active, then you can see the output Y0 and Y1 both are low. Okay, when I2 is active, then output Y1 is high and output Y0 is high and Y1 is low. You can see when input I2 is active, then output Y0 is low and Y1 is high, and when input I3 is active, that time you can see the output Y0 and Y1 both are high. Okay, now let's jump for the RTL design implementation of 4:2 encoder by using System Verilog on a Vivado tool. So here you can see my screen. I have already written a System Verilog code for the RTL design implementation of 4:2 encoder. So let's go through the code. Okay, here you can see my tick time scale is 1 nanosecond divided by 1 ps, and my module name is encoder 4:2. As we have seen in truth table that we have 4 inputs and 2 outputs. So our input is I0, I1, I2 and I3, and 2 output, that is Y0 and Y. Okay, and as encoder is a combinational circuit, so here I have used combinational procedural block, that is always COM. Okay, inside that you can see the cases statement. Okay, and as per the truth table I have implemented the logic here. Inside the cases statement we are having 4 inputs, that is I0, I1, I2 and I3. And we know the functionality of cases statements, that for every possible output we have to provide every possible inputs. Okay, so here you can see that when my input I0 is active, so that time as per the truth table, Y1, output Y0 and Y1 both are low. So here you can see I have implemented here, when my input I0 is active, then output Y1 and Y0 are both are low. When the input I1 is active, then output Y0 is high and output Y1 is low. When input I2 is active, then output Y1 is high and output Y0 is low. Okay, that is represents my active I2 is high. Okay, and when input I3 is active, then output Y1 and Y0 both are high. Okay, and by default output Y1 and Y0 are low. Okay, now when I execute this code, then it give me the schematic like that. Here you can see my input I0, I1, I2 and I3. These are nothing but the registers, and output Y0 and Y1. Okay, now to verify this 4:2 encoder, I have written a simple test bench code. Okay, so let's go through the test bench code also. Here you can see my here also the tick time scale is 1 nanosecond divided by 1 ps. Okay, and the module name is TB4 encoder 4:2. Okay, and here also I have taken the same inputs and outputs, that is I0, I1, I2 and I3 are the input. Output are the Y0 and Y1. Okay, test bench input ports and output ports are same as the DUT input and output ports. Okay, so due to that, here you can see the instantiation encoder 4:2 and duty instance, and here I have used a wildcard operator. Okay, if our test bench input and output ports or duty input and output ports are same, then we can instantiate with dot star, or it will automatically instantiate all the signals. Okay, now inside the initial begin, I have assigned value to the input signals. Here you can see initially I have assigned 1 to the input I0, means right now my I0 is active. At that time all the inputs are inactive. Okay, after 20 nanoseconds I input I1 is active. After 20 nanoseconds input I2 is active. After 20 nanosecond input I3 is active, so that I can verify all the combination. Okay, now if I click on this run simulation, then it will give me the waveform. So I already run this. Here you can, if I click on untitled, so here you can see the waveform. Here you can see the input I0, I1, I2 and I3. So when my input I0 is active, that time you can see my output Y0 and Y1 are low, as I implemented in a logic here. Okay, similarly when after 20 nanosecond you can see my input I1 is active. So when input I1 is active, output Y0 is active and output Y1 is low. Okay, this represents my input I1 is active. Okay, when I2 is active after 20 nanosecond, you can see Y0 is low and Y1 is high. Okay, this represents my I2 is active, and when I3 is active, then you can see my output Y0 and Y1 both are high only. This represents my input I3 is active. And as in by default I have mentioned like output should be 0 0. So here you can see when all the inputs are 0, my output Y0 and Y1 0, and when all the inputs are high, then also output Y0 and Y1 both are low only. Okay, so basically in this video we have discussed about the working and functionality of encoder and the RTL design implementation of 4:2 encoder. So if you are watching this video, then please click on the like